So what actually is simple harmonic motion? So it's a physical action in which a particle is oscillating. So again, keyword of oscillating about a fixed equilibrium position. Again, key term there, and goes through two extremity points, which are the same distance away from the equilibrium position. So if you think of a grandfather clock's pendulum, for instance, it'll swing to these two extremity points, which are the same distance from the equilibrium position. So when the pendulum is actually flat and is not moving, this is what we consider our equilibrium position. And of course, if these move up the same distance, then this angle in here, theta, will be the same. So we have actually seen pendulums in the energy chapter when doing the conservation of mechanical energy. We won't necessarily be using that now with simple harmonic motion, but we can use energy principles in a way. So simple harmonic motion is actually governed by sine and cosine waves. As you can see, this will go up and down, back through it. We have the equilibrium positions, and then we have our two extremity points. In maths, we refer to these as turning points. And if you simply have the graph y equals sine x as your equation for simple harmonic motion, then the slopes here will occur when dy by dx is 0, or the rate of change of the slope is 0, which happens to be at x equals pi on 2 plus 2 pi n, where n is greater than or equal to 0 for all natural n. So with simple harmonic motion, we have to kind of consider pretty much every scenario to do with the particles. So it could actually start up top, for instance. So the grandfather clock could actually start up here and swing down and not just be sort of stationary given an initial push. We also have to consider how fast the motion is going, as well as how the sort of distance away from the equilibrium position is. And this is the equation that governs it. X equals a sine of omega t plus epsilon. You may see this epsilon written as alpha. So written as x equals a sine of omega t plus alpha. I tend to use epsilon because it doesn't really get used that much. Alpha tends to get used for angles and stuff. So, the equation, what does it mean? So again, I'll write it up here. X equals a sine of omega t plus epsilon. So A represents the amplitude. So it's essentially how big the motion is, or essentially the distance between the fixed and the one of the extremity points. So even if you remember from normal maths that if you have y equals 3 sine x, it's going to oscillate. So this is your normal sine wave, and I'll get a new sine wave in blue. So this will now be 3 times higher, but at the same time 3 times lower. So this is going to be your 3 sine x up here. So next, omega is sort of similar in a way to the omega you met in circular motion. However, it's slightly different in a way, in that it's known as the angular period. Now, that's a different shade of red. So it's a bit weird that omega represents two very similar things. However, the relationship of omega is 2 pi over t, or t is 2 pi over omega. Those both still hold true in simple harmonic motion, where t is the time for one complete oscillation. So you can think of omega as sort of seconds per oscillation. Well, that's t. So oscillations per second in a way. So yeah, so this t and this little t and big T mean different things, where little t is actually the time after we started tracking, whereas capital T is time for one complete oscillation. Lastly, we have epsilon, which is a thing known as a phase shift. So this accounts for if the particle doesn't start at its equilibrium position. So if it started at its equilibrium, you'd have something like this. If it didn't start at its equilibrium, it would end up with something like this. You're essentially just moving the sine wave across. And a special case occurs when epsilon equals pi on 2, since sine of omega t plus pi on 2 is the same as cos of omega t. And this would start right at one of the extremity points and let go. So hopefully that should clear up this bit of a monster equation.